Wait. What's happening? Wait, how did you get here? Wait, who told you to get? Oh, I see. You're here to see my self-driving simulation model, which allows the car to avoid the obstacles by itself. This is completely autonomous. Okay, I see now. That's why you're here. Well, if you are, you're in the right place and you're going to see in depth how this car actually works to avoid these obstacles, even if it's just by a slim. So to start, we must look at the environment where the car will actually be driving. As this is all the camera can see because the car is equipped with 360 degrees cameras. So we must place these cameras in correct locations. So to start, we have to look at the import math and from random import radius. This is basically saying how the environment is going to be 2D by just showing the top view of the car, which is what we can see, us the viewers. It uses a combination and mathematical calculations to detect obstacles using rays, which could also be known as LiDAR. This is an actual vehicle to dynamically adjust the car's movement and direction depending on its location. So, as we can see, this is clearly talking about the vehicle's thought process to handle data input and output. So, if we go to the GitHub, we can see that this class is basically defining the car's behavior, portraying the way it applies all of this data on the actual obstacle course, which would be classified as a road in a real environment. It initializes with its position, direction, and maximum turning angle to operate properly without hitting something. As we can see, the car is actually barely skimming, actually avoiding them. It creates rays as sensors for detecting obstacles and updates the car's position based on its speed and direction, which would be person to everything, calculating its surroundings. The rays are recalculated each time the car moves to ensure they reflect the current environment. The update guidance, as we can see over here, actually is a method that biases the car's direction toward the ray with a long unobstructed path, enabling obstacle avoidance. So to define the ray class, which is over here, it basically simulates a line extending outward from the car. Rays calculate the distance to the nearest obstacle by checking for intersections with walls. If a wall intersects with the terminus and the distance is updated then. If no intersection is detected, the ray extends to its maximum length. This allows the car to sense obstacles and adjust its behavior accordingly. The car updates its position and adjusts its direction based on input from the rays, which detects obstacles by calculating intersections with the walls. So these walls, as we can see, play a big role. The rays are recalculated each time the car moves, ensuring that the simulation remains dynamic and responsive to the changes in the environment. This combination of ray-based sensing and movement adjustment allows the car to mimic basic obstacle avoidance techniques, which is pre-trained by the model. Now moving on to the track boundary creation, which is basically this definitely create ellipse. So this is the center, where we can see that the function generates a series of points forming an ellipse, which is a circle, centered at the specific location, which would be the car. It calculates the x and y coordinates of points along the ellipse using trigonometric functions, with major axis and minor axis determining its width and height. These points are stored in a list and returned to define this path of the road. This function basically creates perpendicular points spaced at a given, representing boundaries for the track and each segment of the road, which is why it is crucial because autonomous driving has to be very precise. This ensures the road has defined outer and inner edges as the road curves depending on where the car is. So in the main function of the program, it initializes Pygame. So as we can see, the import Pygame, this is one of the most crucial parts of how this simulation actually works. So this simulation is setting up the environment, which would be known as the track in this scenario. The display dimensions for this simulation would be defined at 900 by 600 pixels, which is why at the beginning of the video, the game was actually simulated at like a smaller window, which was not maximized. And this screen would be created using Pygame display set mode, which is located right here, which is how the code actually runs with the width and height. A clock object is initialized to regulate the frame rate as the car and track images are loaded and scaled to the appropriate sizes using the pixels that were provided by below, 900 and 600. An instance of the car class, which we talked about earlier, is created at positions with an initial degree of 90 degrees, as the car doesn't always turn 90 degrees depending on its location, on where it is located, and a maximum turning angle of 5. So, as this would make sense because we wouldn't want it more. The car rays are updated by utilizing the command Carl update walls, which would be located right here with the Carl update walls. And this basically reflects the current environment. So as we can see, the drive false. So this is basically the autonomous driving section, allowing the car to do game loop, which handles the user's inputs and updates the car's state to match what we want it to be in. By game loop, what I mean is that the outcome of the car is the same from the car, but it's not hitting any of the objects but following a similar path, even if it means changing just a bit. As we can see on the repetition of the car game that I showed before, the car was changing, but the path was very similar. So, as we can see, it continuously checks for events such as quit to close the program and mouse button up, which was also another command, toggling the car's movement. The drive button is a variable that determines whether the car updates its position and sensors. When drive is set to true, the car's behavior is dynamically updated based on the environment and its ray sensors, which was talked about earlier. The steering angle, throttle, and speed are extracted and converted floats for further calculations, while the image is sent to the base64 format, which was pre-coded by this GitHub user. The game loop handles user inputs such as toggling the car's movement and dynamically updating the car's position and behavior when driving is enabled. The program also renders the car and track on the screen as it updates the visuals in real time, which is why it is crucial for these cameras to actually be on the car, as this is basically the car's eyes, which just like how we have eyes. So this basically wraps up the coding part of this project and how it actually works. We used this map, which was shown earlier in the video, and we used this car, which was also shown earlier in the video, giving more of a 2D perspective. Make sure you keep in track with my YouTube channel by turning your notification bell on, and if you are interested in this content, more will come in the future. So here is a last piece of looking on this. Yeah, as we can see, the car is barely avoiding. I will be producing more content like this in the future, so make sure you keep watching. I really appreciate the time that you took out of your day to watch this and educate yourselves. So until next time, see you.